Okay, so the principle which you will have to use is essentially mass conservation, because the gap, the size of this gap here decreases because the plate is falling. This liquid here, the fluid here, whether it's air or water, is being squeezed out. And this is simply by mass conservation. So you only need to think about mass conservation. So that's one part of the answer. And then in terms of the control volume that you can pick, well, you have really a lot of choice over which control volume you can pick. So I'm going to give you 3 examples, and they're all going to look the same, but they're all actually different. Okay, so let's look at the first control volume. The first control volume which you could pick is the following here. I'm taking this control volume, and then I'll tell you exactly what it is. So this is my control volume. This little pie here is my slice of pie is my control volume. And what is important in this control volume is that the control volume, the boundary of my control volume do not change. So this control volume here is independent on time. That's your first choice. And the top boundary of the control volume coincides with the position of the plate. So it's really at the position of the plate, which means that later on, as time increases, the plate is going to come inside of my control volume. So later on, the plate is going to be here, for instance, and it will be inside of the control volume. So now, when you apply mass conservation, you have to think about the mass which is inside of the control volume, just the mass of liquid which is inside of the control volume, and impose mass conservation. This is the first possibility for control volume. Now, the second choice of a control volume which you may have, which you could have picked, maybe some of you picked that one, and this is also a possibility, is the following. So the bottom surface is the same. It really coincides with the wall, and then this is also a piece of my control volume. And now the top part, it looks like it coincides with the top plate, but it doesn't exactly coincide with the top plate. It's a little bit underneath, so it's an infinitely small amount underneath the surface of the top plate. Here again, so I'm just exaggerating here, but you have to assume that this is a dx, so it's negligible. This is my control volume. This control volume is also independent on time, but because it is just infinitesimally by a very small amount, small distance underneath the surface, when the plate falls, it doesn't cross the top boundary of the control volume. So those control volumes are almost the same, but not exactly the same. So again, this top surface here, the top surface of your control volume, you have to assume that it's a differential element of displacement underneath the actual position of the plate, such that when you're thinking about the plate moving, it doesn't enter the control volume. That's your second choice for a control volume. And now your third choice would be to take a control volume which changes with time. You can also do that. So this is my control volume now. The bottom surface is the exact same. The side surface as well. And now the top surface here coincides with the plate, but follows the motion of the plate. So now your control volume is no longer a control volume which is independent on time. It actually does depend on time. So CV, control volume, is a function of t, where the top surface here follows the motion of the plate. So you can pick any of those three control volumes and then try to solve the problem.